Hello dear students, and you are welcome back to our course. As you can remember, my full name is Magawina Gulbakhat Muratовна. So today we have a new topic in Module 3, Chemical Bonding in Inorganic Compounds. In this lesson, we will dive into the different types of chemical bonds, such as ionic, covalent, and metallic, and explore how atoms come together to form stable compounds. Understanding these bonding principles is essential for grasping how inorganic compounds behave and interact in chemical reactions. Let's get started. Ionic bonds. Electrostatic attraction. Ionic bonds form between metals and nonmetals through electron transfer. One atom becomes a cation, the other an anion. These bonds are typically strong due to the electrostatic attraction between oppositely charged ions. Ionic compounds often have high melting points and are good conductors when dissolved or molten. Here are some common examples of ionic compounds: sodium chloride, table salt, it's like common name or like example, magnesium oxide, magnesium, calcium carbonate, chalk, and potassium chloride, potash. These compounds are formed when metal atoms transfer electrons to nonmetal atoms, creating oppositely charged ions that attract each other, forming stable ionic bonds. Covalent bonds, electron sharing. Formation. Covalent bonds form between nonmetals through electron sharing. Atoms achieve stable electron configurations this way. Types. Single, double, or triple bonds can form depending on the number of shared electron pairs. Properties. Covalent compounds often have lower melting points and are typically poor electrical conductors. There are three main types of covalent bonds, depending on how the electrons are shared between atoms. Single bond, one shared electron pair, example, hydrogen gas. Double bond, two shared electron pairs, example, oxygen gas. Triple bond, three shared electron pairs, example, nitrogen gas. Each type of covalent bond plays a role in determining the physical and chemical properties of molecules. Metallic bonds. Structure. Metallic bonds involve a sea of electrons surrounding positive metal ions. Electrons are delocalized throughout the structure. Properties. These bonds give metals their characteristic conductivity, ductility, and malleability. Metals often have high melting points. Examples: pure metals like iron, copper, and aluminum exhibit metallic bonding. Coordinate covalent bonds. Formation. One atom provides both electrons for the bond. The other atom receives them. Characteristics. Similar to covalent bonds but with unequal electron contribution, often seen in complex ions. Example, ammonia, NH3. Bond polarity. The difference in electronegativity between bonded atoms determines bond polarity. Polar bonds have uneven electron distribution. Non-polar bonds have even distribution. Bone polarity contributes to overall molecular polarity, affecting properties like solubility. Intermolecular forces are the forces that exist between molecules, influencing their physical properties such as boiling point, melting point, and solubility. These forces are generally weaker than the chemical bonds within molecules, but play a crucial role in determining how molecules interact with each other. And there are several types of intermolecular forces. Hydrogen bonding, strong attraction between H and the electronegative atoms like N, O, or F. Dipole-dipole, attraction between polar molecules, weaker than hydrogen bonds but still significant. Van der Waals, weak forces between all molecules, including London dispersion forces. For instance, water has strong hydrogen bonds, which is why it has relatively high boiling point compared to other molecules of similar size. Applications in material science. Ceramics. Ionic and covalent bonds create strong heat-resistant materials used in various industries. Alloys. Metallic bonds in mixed metal systems produce materials with enhanced properties. Semiconductors. Covalent bonds in silicon and germanium enable modern electronics and solar cells. Nanomaterials. Understanding bonding at the nanoscale leads to novel materials with unique properties. Understanding these forces allows scientists to create materials with tailored properties for scientific, industrial, technological, and biomedical applications. So, my dear students, thank you for your engagement throughout this lesson. I hope you now have a clear understanding of how atoms bond in organic compounds and how these bonds shape the chemistry of life. And the next time we are going to talk about acids, gases, and salts. Thank you for your attention. Goodbye.